In this video, we work a second example of the solution method for an exact differential equation. We've got an equation that looks like this. This time we also have an initial condition. This is modified from problem 3 of section 2.6 of the Constanda differential equations textbook, a primer for scientists and engineers. And I believe this is the first edition. I think they might be on a second or third edition now, but this is what the book looks like. I really love this book. It's sort of like simple and no frills, but like it's just well articulated, and I'm a fan of that book. This is, I claim, an exact differential equation. Remember how we can tell if this is an exact differential equation? This is an exact differential equation if this left-hand side over here is the exact differential of some function f. If I label this function m of xy, and I label this function n of xy, it turns out that this differential equation is an exact differential, or is an exact differential equation if the derivative of this function with respect to y is equal to the derivative of this function with respect to x. Now, if you're not sure like how to remember which one is which, it's not the variable that's multiplying it, but it's the other one. So I want to take the derivative of this function, not with respect to x, but with respect to y. And I want to take the partial derivative of this function, not with respect to y, but with respect to x. If those two are equal to each other, then the differential equation is exact. So we'll start by doing that. So you're going to compute the partial of m with respect to y. That's how we notate that with subscript notation. And the partial of n with respect to x in subscript notation. If they're equal, it's exact. So the partial of m with respect to y, which can also be written this way if you prefer Leibniz notation, that's fine, is this. So partial with respect to y of 3x squared times y to the negative 2 plus x to the negative 2 times y squared minus 2x to the negative 3. And the derivative of this with respect to y is pretty straightforward. You want to treat all the x's like constants, and you're differentiating with respect to y. So this 3x squared is a constant. So it's a constant times y to the negative 2. So I can bring my constant down and then multiply by the derivative of y to the negative 2. We just use the power rule to bring the power down, multiply by y to the 1 less power. And over here, this x term is, or this x factor is a constant. I've got a constant times y squared. So I bring my constant down, and then I multiply by the derivative of y squared with respect to y. That's 2 times y. And the derivative of this with respect to y, well, if x is a constant, the whole thing is a constant. The derivative of constant with respect to y is 0. So that piece is gone. And if we simplify this, we get negative 6 x squared y to the negative 2, or negative 3, excuse me, plus 2x to the negative 2 times y. Okay, so that's that partial of m with respect to y. Now let's take the partial of n with respect to x, see if we get the same thing. You can use subscript notation if you prefer, or you can use Leibniz notation. Just want to point out, this is a function, and this is a function. This is not a function, this is an operator, so it's a little different. This is the partial of m with respect to y, which is a particular function, it's this. This says, take the partial with respect to y of whatever's in the brackets in front of it. So be very careful about that. We're saying this is a function, and we're calling it the partial of n with respect to x, or we can notate it this way, the partial derivative of n with respect to x is equal to the partial derivative with respect to x of whatever n is. And I'm going to fill that in right here. Now we're treating x as a constant, or y as a constant, and x is our variable this time. Now there are no x's here. So the derivative of this is just taking the derivative of a constant with respect to x. We just get 0. Now I've got over here, I've got a constant times x to some power. Now remember, whenever you take the derivative of a constant times a function of x, you bring the constant down, and then you take the derivative of that function of x. So I focus on the x cubed, and I take the derivative of that. By the power rule, that's 3 times x to the 1 less power, so that's 3x squared. Over here, again, I've got a constant times a function of x, so I'll bring my constant down, and then I take the derivative of that function of x. Derivative of x to the negative 1 is negative x to the negative 2. And then we'll simplify. We've got negative 2 times 3 is negative 6, and for whatever reason, mathematicians, I guess we just like things to be orderly sometimes. We tend to put the variables in alphabetical order. So we'll have negative 6x squared times y to the negative 3. And then a negative times a negative is a positive there. So we've got positive 2, and we put the x's before the y. And now I'm just comparing this function and this function. Those are the same. Those are the same. That's great. Since those two partial derivatives are the same, we can conclude that the DE is exact. Okay, and then we want to state what that means. When we say a differential equation is exact, what we mean is that there is a function out there, f of xy, such that the differential of f is the left-hand side of that differential equation. It's m dx plus n dy. And remember, this little backwards e just means there exists. So you can write that if you want to, or you can get used to that mathematical shorthand. I think people kind of like once you know what it means. So there's some function out there for which this is true, and we're trying to find that function, because if we have this equals 0, the differential of f equals 0, then f of xy equals a constant is the solution of our differential equation. So there's some function for which this is true, and the differential of f is defined to be this, the partial of f with respect to x times dx plus the partial of f with respect to y times dy. The only way that's true is if these functions are equal and these functions are equal. So that means that the partial of f with respect to x must be m, which was this function, is the function multiplying dx at the top. And the partial of f with respect to y must be n, and that was this function. That was the function that was multiplying dy at the top in our original differential equation. Okay, now we're trying to get f back, and we have its partial derivative with respect to x and its partial derivative with respect to y. Now, each of these will allow us to recover f, but only partially. So you kind of have to put the two pieces together to find what f is in general. If I want f and I've got its partial derivative with respect to x, I need to take the partial antiderivative of the partial of f with respect to x with respect to x. So I'm undoing that with anti-differentiation. Now remember, here you are treating x as your variable and y as a constant. So the antiderivative of this piece, well, I'll bring my constant down because I've got a constant times a function of x. And then I want the antiderivative of x squared with respect to x. So we're going to use the power rule. Add 1 to the exponent, divide by the new exponent. Then I've got a constant times x to the negative 2, so I'll bring my constant down. Y is being treated as a constant. And then we'll use the power rule for this one as well. Add 1 to the exponent, divide by the new exponent. Bring that negative 2 down, that's a constant. Then we add 1 to the exponent and divide by the new exponent. Now you want to add c. Everybody wants to add c here. But remember, this is a partial antiderivative. So I need something that's constant with respect to x, but not necessarily with respect to y. I'll just call that g of y. And then let's simplify this a little bit. The 3's reduce, and we like to list our variables in alphabetical order, so we'll do it that way. Same thing here. And the -2 divided by the -2 would make that a +2, or a +1, excuse me. So that recovered f partially, gave us almost all of f, but there's some function of y out there that might be part of f. We need to find out what that function of y is. In order to get all of f, I need to do the same thing with the partial of f with respect to y. So if I want f back and I have its partial derivative with respect to y, I take the antiderivative of that with respect to y. Bring the constant down, then add 1 to the exponent and divide by the new exponent. X is being treated as a constant. Bring the constant down, add 1 to the exponent, divide by the new exponent. Again, x is being treated as a constant. Bring the constant down, add 1 to the exponent, divide by the new exponent. And we don't want a plus c here. We want a function that's constant with respect to y, but not necessarily with respect to x. So we're going to call that h of x. And a lot of students are saying, what do you mean by that? And like they can kind of memorize it, but they don't know why. Remember, if you take the partial derivative of this with respect to y, you're supposed to get this back. The partial derivative of this term should give you that. The partial derivative of this term should give you that. And the partial derivative of this term should give you that. And if you've got a function of x over here, the partial derivative of that with respect to y should be 0. That's why it can't just be a constant of integration. When we're taking the partial derivative of this with respect to y, any function of x with respect to y, we would get 0. And if I'm taking the partial derivative of this function of y with respect to x, I'm going to get 0. So it makes sense that we would have a function of y here and a function of x here. Okay, so I'm going to simplify. And then the -2 divided by the -2 is a +1. Okay, now both of these are f. The same f. This is equal to this. So we want to find out what f is in general. So the first thing I do is I write down anything that matches. I've got an x cubed y to the -2 here, and an x cubed y to the -2 there. So they both have that. And a negative x to the -1 times y squared on both of those. And then I have the part that doesn't match. Then I have x to the -2 plus g of y, and then this piece. A -2 y to the -3 plus h of x. These have to be the same. Well, I think if g of y were this function of y, and if h of x were that function of x, that would work. And of course, we could have an arbitrary constant in there. So maybe g of y is this plus a constant, and h of x is this plus a constant. So f of xy is going to be this, those parts that match, that are exactly the same. And then through matching, we see that f of xy must have an x to the -2 term and a -2y to the -3 term plus c. Now let's check and make sure that this works for both of them. The question is, this red part, is that x to the -2 plus a function of y? Get an x to the -2 plus a function of y. Yes, so it checks out. This is equal to this. This whole thing is equal to this. Now the other question is, okay, this red part, is this the same as this function plus a function of x? Well, you've got that, and then you get the x to the -2 plus c, that's a function of x, yes. So this checks out. This is this and this at the same time. So that is not the solution of the differential equation. Remember that the solution of an exact differential equation is a level curve of some surface. So I'm just going to draw that elliptic paraboloid again. or elliptic paraboloid. This mine didn't go through the origin this time. If my function is z equals f of xy, and f of xy is equal to a constant k, like let's say k is 20, so z is equal to 20, and I take the differential of both sides, I'll get df equals the differential of that constant, which is 0, and df is m dx plus m dy, and that's going to be 0 for the original differential equation. So the solution of this guy is this guy. It's not just f. It's f of xy equals a constant, and I'm calling that constant k. And if you're wondering again what this picture is, this is just where z is equal to f of xy. And I'm just showing a curve where z is equal to a constant k. All right, now that's actually not what this surface looks like at all. But the solution of the differential equation is this function equals k, and we'll let the k on the right-hand side absorb the c. So we'll have x to the third times y to the negative second minus all of this. I'm not going to read it to you. Equals k. That's the general solution of the differential equation. Or if you prefer, you can call it an implicit solution if you're thinking of y as depending on x, but we're really not thinking of it this way. We're thinking of it more as a level curve of some surface. Okay, now we have an initial condition this time. So this is going to allow us to pick out the right value of k. This says that when x equals 1, y equals negative 1. So to find the actual solution curve, so we have a specific value of k, not just an arbitrary k. We're going to use the initial condition to find the value of k. So y of 1 equals negative 1 means the following. It means that when x equals 1, y equals negative 1. And you can substitute 1 for x and negative 1 for y over here, and that's going to tell you what k is. So we've got x cubed, and I'm going to write this with the negative exponents. I'm going to put those factors, in the denominator. So we have x cubed, which is 1 cubed, over y, which is negative 1 squared. And then over here we have minus y squared, so negative 1 squared, over x, which is 1, plus x to the negative 2, that's 1 over x squared, and x is 1, minus 2 over y cubed, and y is negative 1, and that equals k. Let's just do a little bit of simplification. So this is 1, the whole thing, and this is 1 over 1. So I have minus 1 here, 1 minus 1, that's 0. Then I've got a plus 1, and then I've got a minus 2 divided by negative 1, so that's plus 2. So it looks like k equals 3. K is equal to 1 plus 2. Now, I should probably state my final answer. You don't just say k equals 3 and you're done. The final answer is this function, this equation equals 3 because k is equal to 3. Normally I would write it again and I would substitute it, but I ran out of space on my paper. So I'm just going to cross it out like that. So this is a level curve on a surface that's given by this function. And we're saying, well, when is the z value on that surface equal to 3? Like that curve, that's the solution of this differential equation. If I take the exact differential of this side and the exact differential of this side, the exact differential of the left-hand side is this, and the differential of 3 is 0. And the point x equals 1, y equals negative 1 lies on that curve.